Good day, class. So today we're going to talk about the types of functions. So we have a lot of types of functions, but we're going to talk about some types of it. So we have the polynomial function, the linear function, the quadratic function, the constant function, the rational, radical, exponential, logarithmic, and piecewise defined function. So first, polynomial function. So for the polynomial function, we have to remember that this is defined by this equation. F of x is equal to a sub n x raised to n plus a sub n minus 1 x raised to n minus 1 plus ellipses plus a sub 0 such that a sub n, a sub n minus 1, ellipses until a sub 0 are real numbers. Okay, and x raised to n, x raised to n minus 1, ellipses until x are they are the variables. Okay, and we also have to note that in this polynomial function, the n here is a non-negative integer. Okay, so let's have an example of a polynomial function. For example, this one. Okay, so f of x is equal to x squared minus 2x plus 1. Okay, so we have here the a sub so another example of polynomial function is g of x is equal to 2x plus 1. Another example is square root of 3x cubed minus square root of, let's say, 1 or 14. So these are examples of polynomial functions. Okay, so next, linear function. So in linear function, from the term itself, the graph of the linear function is a line. Okay, so for this, the linear function is defined by the equation f of x is equal to mx plus b, such that this m is called the slope, while this b is called the y-intercept. Okay, so if m is positive, let's see, like this, if m is positive or if the slope is positive, the graph of the line is like this. Sorry. If m is positive, the graph of the line is like this. Okay, so it's color blue. So it's going upwards. So from left, from the down or lower left going to the upper left. Okay, from lower left going to the upper left. Now, if the slope is negative, our graph would be like this. So from upper left, it's going downward to the lower right. Okay, understood? Okay, let's proceed. So again, the graph of the line or the linear function is a line. Okay, for the next function, it's quadratic function. So quadratic function is defined by this form. So f of x is equal to ax squared plus bx plus c. So this is the standard form of the quadratic function. And you have to note that the degree of the quadratic function is 2. Okay, when we say degree, it means the highest exponent. Okay, so in quadratic function, the highest exponent is 2. While in the linear function, the highest exponent is 1. Okay, now
the graph of the quadratic function is called the parabola. So what does parabola look like? So it's like this. So this is our xy plane, and let's mark it maybe color blue. So the parabola looks like this. Okay, so it looks like a smile, but it could also be like this, uh, a frown. Okay, ngayon, if the parabola um, looks like a smile or it goes upward like this, above, meaning our or the coefficient of x squared, coefficient of x squared is positive. Okay, so example is 2x squared minus x plus 1. That's an example of a quadratic function such that the parabola, the graph of the parabola is going upwards. Now, the one below, this one, so for this, the coefficient of x squared is negative, okay? Negative coefficient of x squared. So example for this is uh, neg negative 2x squared plus 2x minus 1. Okay, so our coefficient for x squared is negative 2, which means that the parabola is going downwards. So like this. Understood? Okay. Next is we're going to have the constant function. So for the constant function, it's still a polynomial function, and it is defined by the equation f of x is equal to c. So c here is a value, any number. For example, f of x is equal to 1, f of x is equal to 4. So any number such that c is a real number. Okay, so this one, it means c is a real number. Okay, any real number. So let's give an example for this. So for example, f of x is equal to 1. So according to the slide, the graph of this is a horizontal line. So how do we graph it? Okay, so we have the xy plane and we graph it. Okay, so the way we graph it, according to this one, a horizontal, so this is 1, and our graph for this is this. Okay, so this is f of x equals 1. So for any domain here, any value of x here or any domain, our value is always 1. Okay, understood? It could also be in the lower part of the y value. So it could be here. So for example, negative 2. Okay, so it could be like this. So for this one, any value of x again is negative 2. Okay, so this is f of x is equal to negative 2. Understood? Okay, so next we have the rational function. So for the rational function, it is defined by the equation f of x is equal to g of x over h of x, such that h of x could never be 0, and g of x and h of x are both polynomial functions. So for this one, basically what we should know is the rational function is, it looks like a fraction, okay? You have the numerator and the denominator, and these numerator and denominator should be polynomial functions. Okay, so let's just write it. Oops, over h of x. Okay, so this one, g of x and h of x, should be a polynomial function. Okay, let's just represent p of x as a polynomial function. Now let's provide an example for this. So f of x is equal to, let's say, x plus 1 over x minus 1. So we say that this is a rational function because the numerator for this is what? This is a polynomial function. Polynomial function there. And x minus 1 is an example, of course, of polynomial function as well. So if we use, or if we go back to the definition, this equation, f of x is equal to x plus 1, satisfies the definition. So this is a rational function. So f of x is equal to x plus 1 all over x minus 1. All right. So the graph for this is not stated, but we have to note that in rational function, there exists what we call as an asymptote. Okay. Asymptote is a line where our graph goes near that line, but it never touches it. Okay, so we have here the vertical asymptote. We also have the horizontal asymptote, and we also have the oblique asymptote. Later on, we're going to talk about the graphing of the rational function. But for now, we just have to know that this rational function has an asymptote. Okay, so what does the graph look like for this? So we have here, again, the xy plane. So for example, for the rational function, we have here the vertical asymptote here. Just imagine it as a straight line, okay? And the horizontal asymptote here, okay? So now for the graph, let's say the graph of this is like this, okay? And of course, this one, okay? So for this one, we can see that the arrow goes upward here. And when it goes upward, it gets nearer and nearer to, it gets closer to the asymptote. Okay, same for this one, this one, this one. But again, these curves do not cross the asymptote, do not touch these asymptotes. All right. Okay, let's proceed to the next one. Radical function. So radical function, by the term itself, what we can see from here is a radical sign. So it is defined by the equation f of x is equal to g of x, or nth root of g of x. Okay, so g of x, the one inside the radical sign, should be a polynomial function. Okay, and the nth root, or the n there, is a non-negative integer greater than 1. Okay, so we have here the non-negative, and we see non-negative means that n should be positive, n should be greater than or equal to 0. Okay, we also have here integer, Okay, it means that it should not be a fraction. It's just 0, 1, 2, 3 ellipses. But also, we also have another characteristic. It should be greater than 1. So let's just remove this one and this one. If it's greater than 1, it starts with 2, 3, 4 ellipses, any number. Okay, for as long as it's non-negative and integer and greater than 1. All right, so let's give an example for this one. So f of x is equal to square root of x. Okay, so the n here is 2. X is a polynomial function. Under example, g of x is equal to cube root of 2x plus 1. So the n here is 3. And the polynomial function here is 2x plus 1. Alright? And last example is fourth root of x squared plus 4 minus 1. Okay, this is an example of a radical function. Okay, so the n here is 4, and the p of x here is x squared plus 4. Alright, again, in radical function, what we need to remember here is that we have to look for the radical sign. The radical sign looks like this. Alright, okay, so next one, exponential function. So for the exponential function, it is defined by the equation f of x is equal to a raised to x, such that a is greater than 0 and a should not be equal to 1. Okay, so f of x is equal to a raised to x. The a here is any number that satisfies the one in the definition a while ago. So it should be greater than 0 and it should not be 1. Okay, so this is what we call the base in the exponential function. And then the x here is called the exponent. Okay, so since this is the exponent, this is any variable. So it could be x, it could be x plus 1, it could be x plus 2, or 2x minus 1. Alright, for as long as this form f of x is equal to a raised to x can be observed in an equation, then it is called an exponential function. Okay, let's give an example for this. So basic example for this is f of x is equal to 2 raised to x, right? Another example, f of x is equal to 5 raised to x minus 2, right? So this is called an exponential function. Another example is g of x is equal to 3. So 2x plus 1 minus 1. All right. So how about this? H of x is equal to x squared plus 1. Is this an exponential function? So in this case, this is not an exponential function. Okay? Why? Because the base here is a variable. Okay? And in fact, x squared plus 1, though it's not an exponential function, this is actually a quadratic function, okay, because it has a degree. What's the degree? It has a degree 2, okay, understood? Okay, next, logarithmic function. So for the logarithmic function, this is defined by the equation f of x is equal to logarithm of x to the base a, where a is greater than 0 and a should not be equal to 1. Okay, so according to this definition, these functions are the inverse of exponential functions. Okay, so um, if you see a logarithm in an equation where in that logarithm there are variables as well, then it is called a logarithmic function. So for example, f of x is equal to logarithm of x to the base 2. Okay, this is a basic example of logarithm. So we have here the elements, the base, the the base, and the one beside the base. Okay, I mean the logarithm, just a variable. All right. So for this one, this is called a logarithmic function. Another example, g of x is equal to the logarithm of x plus 1 to the base 3. Okay. This is again an exponential, I mean an example of logarithmic function. And another example, h of x is equal to logarithm of 3x minus 1. Okay, logarithm of 3x minus 1 is also a logarithmic function. So for this particular example, if we observe that it doesn't have any base, by default, the base of this is 10. Okay, there is a hidden number or hidden base there, just usually not written. The base here is 10. All right, for the logarithm. Understood? Okay. So again, let me reiterate that the inverse of the logarithmic function is the exponential function, and vice versa, the inverse of exponential function is the logarithmic function. Next, piecewise defined function. So for a piecewise defined function, according to the definition, it involves more than one formula. Okay, more than one formula used to define the output over different pieces of the domain. It describes situations in which a rule or relationship changes depending on the input, or what we call certain boundaries. Okay. Okay. So the notation for the piecewise defined function is f of x is equal to um, num is equal to different formulas such that x is in the domain domain 1, domain 2, and domain 3. Right? So let's give an example for this so that we get to appreciate the piecewise defined function. Okay? So for example, f of x is equal to x if x is greater than 0 and negative x if x is less than 0. Oh, let's just add the 0 here in the first equation. So again, f of x is a piecewise defined function where the output is x if x is greater than or equal to 0, and negative x if x is less than 0. Okay, so this is an example of piecewise defined function because it has more than one formula. Another example is g of x is equal to x squared minus 1 if x is greater than 1 and x squared plus 1 if x is less than or equal to 1. Okay, another example, h of x is equal to negative 1 if x is in negative infinity to negative 1, 0 if x is in negative 1 to 0, and 1 if x is in 0 to positive infinity. So as you can see here, I have here the equation given a certain domain, another equation for a certain domain, and another equation for the next domain. Okay, so if, for example, x falls, I mean, for example, x is equal to 1, so the domain falls under this. Okay, since this is greater than 1, in this notation here, x is in 0 to positive infinity, then we're going to use this equation. H of x is equal to 1. Okay, and another, if x is equal to negative 2, let's say, so since this negative 2 falls under this one, the one in the first domain, then we can say that h of x is equal to negative 1. All right. So that's just an example of a piecewise defined function. And according to the last sentence, an absolute value is an example of a piecewise defined function. So absolute value, it looks like this. So f of x is equal to absolute value of x. So how is this a piecewise defined? So we can rewrite this as f of x is equal to x if x is greater than or equal to 0, and negative x if x is less than 0. Okay, so for this one, the graph of the absolute value is, well, it looks like this. Okay, understood? So from this 0 to the positive infinity, this one, oh, sorry. Going back, so for the domain x is greater than 0, this one. So the graph here is this one. But if the domain is x is less than 0, so this one, the graph here is this one. So it has two graphs. So depending on how many number the equations are, these are also the number of the graphs that you will have in the piecewise defined function. All right. Okay, so we have discussed all the types of functions that are necessary for this subject. And as you can see here, these are the different graphs of the um, types of functions that we have. So for the linear, we have here the line. Okay, again for this one, if the slope is positive, it looks like this. And if the slope is negative, then it should look like this. All right. Next for the quadratic. So the graph of the quadratic is a parabola. For this particular graph, it means that the coefficient of x squared is positive. And if the coefficient of x squared is negative, then it looks like this. All right. Okay. This one is constant. So the constant is a horizontal line. Next, for the asymptote. For the asymptote, we have talked about the asymptotes. I mean the rational function. For the rational function, we have talked about the asymptotes. So as you can see here, the asymptotes are actually invisible. So here are the asymptotes. There. All right. Here. Oops. Hmm. Okay. There. There are the asymptotes. So the graph, the color blue here, does not touch the red lines, which are the asymptotes. All right. Next, for the radical function, this is just an example of a radical function. So it goes like this. So from this one, going there, slowly going upwards. In the exponential, um, the increase of the the growth of the line in the exponential or the curve is uh, is kind of fast. Okay, so from this one it goes like this. Unlike the linear function, if for example start here, so the linear function is a bit slow. The growth of the linear function is a bit slow than the exponential function. All right. And then for the logarithmic function, it's just the inverse of the exponential function. The graph looks like this. And for the piecewise defined function, so we have a certain number of graphs depending on the number of equations that we have in the piecewise defined function. So for this particular graph, we have two lines, which means that we have two equations in the piecewise defined function. Okay, this particular graph is called the absolute value. Okay, so I think that's it for the types of functions. Uh, but you so let's proceed with doing some exercise. So I want you to answer these questions. So for this slide, we have to identify the type of function that this equation or function um, for this type of for this function. So first is f of x is equal to 2 raised to x minus 2 plus 3, and so on and so forth. Okay, and then for this one, we also have to identify the given equation or curve. Okay, so okay, let's try to answer this. So for this one, what we can observe for number one is it has exponent, and the exponent has a variable. So this one is called the exponential. Okay. Next, for number 2, we can observe that it has the logarithm sign for this. So this is a logarithm function. And lastly, for number 3, so it has 2 equations and 2 domains as well. So 1 and -1. So this means that this is called a piecewise defined. All right, understood? Okay, let's proceed with the next one. Okay, this one is simple. Okay, so the first one, we can observe that the graph is aligned. So this is called the linear function. Next one, this one, we can observe that it has 2 graphs. Okay, so this one and this one. Okay, so this is called the piecewise defined. Okay, and lastly, for the parabola, so this one is a parabola. So this is a quadratic function. Okay, so I think that's it for the types of function.